Welcome to another video. In this video, we're going to talk about something called proof by mathematical induction. And even though it might sound like a really weird cooking technique, induction is the idea of if I can prove for the next idea, the next term, I create a proof that's very similar to knocking over a domino and having it knock over a lot of other dominoes. Induction is the idea of prove one, prove the next one, and if you prove the idea of the next one, you can always iterate that further and further. Almost like recursion, but in the future. So we're going forward instead of going backwards. Now, here's what the mathematical induction does, and then I'll show you why it works as we go through, because at first it's going to seem like that shouldn't prove a darn thing, but I'll explain it to you why it does. So here's how induction works. Number one, you have to show that at least one term is true. So we're going to show that whatever we're trying to prove is true for at least the first term. So we're going to show that n equals 1 is actually true. Then what we're going to do might seem a little fishy. The next thing we're going to do is assume that it's true for some other number, not 1, but something between 1 and n, whatever n is. That might look a little funny, but here's what this says. It says if you show the first one, then you're going to assume it's true for some other term. So n equals k. Now what's the k? K could be anything. K could be the second term, or the third term, or the fifth term, or the 500th term, or some other number. So we'll assume it's true for something else. So we show it's true for one, we assume it's true for another one, and then we show it's true for the next one. Well, now what would the next one be? The next one would be whatever's after the one you just assumed. So hang on a second. If I assume the third term to be true, then the one that would be next would be 4. If I assume the seventh term, the one after that would be 8. If I assume the kth term is true, then the next one would be k plus 1, the one after it. And this will actually prove the truth of whatever you're trying to show. And we'll talk about why that is as we go through it. One thing to keep in mind, and this is kind of fun, and this is where sometimes it makes your brains go, wait a minute. You would assume this and assume it to be true for fact. Treat this step as fact. It's important, otherwise you can't finish your problem. I always like to treat my assumptions like fact anyway, but here we actually get to do it, which is kind of fun. I'm going to walk you through it. There's no more to explain. You show first, you assume one more, and then you show the one after that. And that's how mathematical induction can be quickly summarized. So we're going to do 2 examples, and I'll show you exactly what I mean. This is probably the most important thing, is treating this assumption like fact. So here we go. First, to maybe get an idea of what's going on. So what is this actually saying? This is 1, 3, 5, 7, 9 odd numbers. The sum of odd numbers is equal to the number of the term of number of odd numbers squared. Whoa, really? Yeah, that's true. So here's what we're going to do. We're going to show the first term. Like n equals 1. You go, all right, well, what would that mean? What that would mean is add up the first odd number, that would be 1. Is that equal to the number of odd numbers squared? That would be the first odd number squared. Yeah, 1 actually does equal 1. That shows that that's true. We've proved the first term true. Now, I'm going to go a little further, but you wouldn't have to. I'm just going to show you so you get a feel for how this series actually works. Now, keep this in mind. What I'm doing is not additionally proving. I'm not doing that. I'm just showing you the formula. This does nothing to prove it. You could show however many you wanted. You'd have to ultimately show that the next term is true. Well, you can't do that, right? Like, you can't keep going forever. So at some point we'd have to stop. We'd run out of time in our lives to show every single iteration of, imagine the 500th odd number being added, or the 5 billionth. Well, you can't do that. You have to set up a series of dominoes and say, if I can show that the next one's true, then the next one will always be true. If the next one's always true, then there's no stopping that falling of the dominoes. So let's do this. How about this? How about adding up the first two odd numbers? That would be 1 plus 3. Is that equal to, these are two odd numbers, n is 2. Notice what we're doing. The first two odd numbers will be found by plugging in 1, that's 1. Plugging in 1, then 2, that's 1 and 3. And then plugging in 2 here, that's 2 squared. 4 does equal 4. That is really kind of cool. If you wanted to find the sum of the first 50 odd numbers, just take 50 and square it. You have it. We're proving that's true right now. I'm going to do two more just so you get the feel. How about the first three odd numbers? The first three odd numbers would be 1 plus 3 plus 5. I've added three odd numbers. 3 squared is 9. That's 9. That's 9. How about adding the first four odd numbers? 1, 3, 5, and 7. Is that equal to the first four odd numbers squared? So 4 squared, that would be the 4 odd numbers I'm adding. And these are the values of the odd numbers. That would be 16. That is 16. It actually does work. Now, I'm going to say this one more time. You could do this forever, and it still wouldn't be enough proof to fundamentally prove that that is true. You would have only shown it for a finite number of values. What we need to do with induction, or what we intend to do with induction, is set up this idea that if I can now prove that the next one will always be true, then I can use that to say, well, the next one's true, but then the one after that will be true, and the one after that will be true. We can only do that by assuming something and proving the next one. That's our next two steps. So in general, we just show this, and then we go, okay, let's assume it's true for another one too. We've actually shown several more, but this is not enough to assume it's true for a general next one. So this is step 1, right here. And step 2 is, now that you've proved one of them, let's assume it's true for something else. Now that something else could be anything past the first one. It could be the second term, or the third term, or the fourth term, or the 50th term. But in general, we would just say, okay, if this was true for the first one, let's rewrite this, but let's assume it's true for some other number. Now, it looks funny in saying let n equal k. All it's saying is assume this, which is based on n, is true for some other term. Call it k. Well, what would that mean? What that would mean is, like I showed 1 plus 3 plus 5 plus 7 is the same thing as 4 squared, I would show 1 plus 3 plus 5 plus 7 plus all the way up to whatever the k is going to equal k squared. That's what it is. It basically replaces n with k, but the idea is more important than that. The idea is what you're doing is you're saying, yeah, that worked for the first one. Is it going to work for a second one, or a third one, or a fourth one? Well, let's assume it will. We showed 3 of them, but let's assume it will. Let's show that maybe it's not the 4th term, maybe it's the 7th term. Then I show 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 15, all the way to wherever I want to stop is equal to that number of odd numbers squared. So we say, assume it's true for k. Okay, well, let's just go up to that specific term and say, yeah, that's going to equal k squared. It's more important than just replacing this. It's understanding I'm showing this for some other term past 1, past your first one. If it was 50, I'd do 1, 3, 5, 7 all the way to 50 equals 50 squared. Whatever the 50th odd number would be. 101? 99. It'd be 99. So I'd show that all the way up to 99, it would equal 50 squared. I hope that makes sense to you. I hope that you understand that I've shown the first one. I hope you understand what this actually means. It's not just replacing it with k. It looks like it, but it's saying, assume it's true, then this would be valid for some other number k, some other term k. Now, the most important part. We are going to treat this like fact. This is true. So whenever we see it come about, and we will, this is going to equal k squared. We can use that. we could use it. So the last thing we do is, now we need to show this. We need to set up a series of dominoes and say the next one's true, the next one's true, the next one's true. So we need to show this for n equals k plus 1. Well, now what would that be? If I show this for n equals k plus 1, then what would happen is I would take this and I would stop not at k, but I'd stop at k plus 1. That's the next one. That's showing the next one's always true. Well, you can't stop that. If you show the next one's always true, then when you get to 1, you show the next one's true. But when you get to that one, the next one's true. When you get to that one, the next one's true. It will go forever, and you'll always be able to prove the next iteration is true. The next term is valid. This holds for the next term. So here's what we would do. We're going to take this and go, okay, if I stopped at k, I would stop at k minus 1, or 2k minus 1. But if I go to the next term, now I'm going to take and not plug in k. That's what this was. I'm going to plug in k plus 1 to there. So this is stopping at k. We're assuming that's true. This is stopping not at k, but notice we have one more term. We have, let's stop at k plus 1. So this is the idea of the next term. I hope that you're seeing that we're taking this and we're going one more further than where we stopped here. For this one, we said, let's plug in k. Let's assume it's true for when we plug in k. Okay? And now we're saying, let's go one more than that. So we're not going to stop at plugging in k. That's here. We're going to stop at the next one, plug in k plus 1. Well, that'd be 2k plus 1 minus 1. That would be the next term. Now, what should that be equal? That should equal k plus 1 quantity squared. Showed it for the first one, assumed it's true for some other one, and now based on this, that's true, show for the next one. So plug in this, assuming this is true. Here's the whole idea. If you can assume that this is always equal to k squared, then wherever you see it, this part is this part. We just want one more term. So why wouldn't it be appropriate to say, if this part is this part, and we know that this is true, because we assumed it, if we know that's true, then this is k squared. Well, we have one additional term. Okay, let's maybe distribute that. 2k plus 2 minus 1. This is 2k squared, or k squared plus 2k plus 1. And so is that. If I distribute it, that shows that this side equals this side. And it's shown that if I have an additional term, if I have the next term, that the formula still holds true. So this is showing that provided I can prove it up to one term, the next term will be true. Now here's why this works, because you might be going, this is fishy because you're assuming something's true you haven't proven. Yes, but we sort of have. Remember, this will hold true for any next term. And since we've shown one term, wouldn't this hold true for the term after that, i.e. the second term? Yeah, it would. So if I just had this, let's make k equals 1, the next term would be 1 plus 1, the next term. So if I can prove one term, if this is always showing the next term is true, then I've already shown one term. This holds for term 2. But wait, if it holds for term 2, I can show the next one. It holds for term 3. Well, wait a minute, if I show term 3, then this holds for the next one. Do you see how I'm knocking dominoes over? If I show just the first domino, and I show that it's true for the next domino, and I use a general term, not to show it here, but show it in general, that I'm knocking over the next domino, and then the next one, and then the next one, and then the next one, it will never stop. That's how induction works. So even though it seems a little fishy, like, wait a minute, you're assuming something you haven't proven. That's true, but we're basing it on the fact we've proven one and showing it that the next one, even if I start with that one I just proved, is always going to be true, thereby going forever as this true, 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 knocking down thing, this array of dominoes falling over. And that's the way induction works. So show one, assume for some other one, and then show the next one, treating this like fact because we've already shown it for one, and it sets up this series of falling down. And that's kind of cool. We can always use this as true. It'll show up somewhere when you're solving it as, hey, replace this with that, and then you show that both sides are equal. Let's do the same thing here, but we're going to be a little bit more concise about it. I'm going to do the very minimum to show you how the induction works. So number one thing with induction, if you're trying to prove this, and by the way, this would prove all of the formulas for your series that you would get. It would prove all of them. Sometimes it takes a little bit more work, but it would do it. So let's show the first one. Does it hold true for 1? So if I plug in 1, I would get 1. Is that equal to 2 times 1 squared minus 1? Remember, I'm showing the first one because I have to have somewhere for this domino to start, somewhere to say, yes, but I proved the next one will be true. What's the one after 1? 2. I've proved the second one's true. What about after 2? I've proved the next one's true. So I've proved the idea of the next one being true. So is this true? If n is 1, would that equal 2 times 1 minus 1? That's 1. Yes, this is true. I've now proved the start that my first domino can fall over. That's too many S's. Assume it's true for something else. So assume it's true for like the second one, or the third one, or whatever one. We use k to represent the idea of another term. So something else besides the first one, we're going to assume that that's true and then show that it keeps on falling, show that the one after that would be true. So we've assumed it's true for something else, that it will hold. And now we're proving an idea. We're proving that the next term will also be true given that this one was true. So if this was true, the next one's true. Now, why is that okay? Well, we've already shown that one's true, so showing that that's true, given that, then another one will be true. The second one. Given that, the next one will be true. We're proving an idea, a concept. Okay, well, if that's true, then what we're going to do is we're going to go all the way to here. We're going to show that in terms of k, and then one more. So all the way to here, and then the next one. We need to show this. We need to show this exact thing because it will come up again. We just did it. And then you need to show the one after that. How you show the one after that is you evaluate. It's basically a composition. You take k plus 1 and you replace that with k plus 1. You've already replaced it with k. Now go to the next one. So it's 4, k plus 1 minus 3. Over here, we do the same thing, but remember, you're replacing it with k plus 1 now. You're talking about the next term. That's how this series is added. It says, take however many terms you have, plug it in there. If I went to 5 terms, I'd plug in 5 and 5. If I went to k terms, I'd plug in k and k. That's what we did right here. Now I'm going to k plus 1 terms. I'm going to plug in k plus 1 and k plus 1. Showed the first, assumed it, assumed this is true for some other term besides n, and now based on that assumption, we said, assume this is true, take it as fact. show it for the next one. So if I show it for the next one, I take k plus 1, I plug it in here. That would be the next term, and that would say, based on my series, I have to evaluate k plus 1 and k plus 1 because that is a term that I'm now showing to be true. So that's what this says. Here's the k, here's the next term, k plus 1. Just evaluate it. And then that would equal, well, the k plus 1 term inside of my sum. So k plus 1 squared minus k plus 1. Hopefully you're seeing where that comes from. Because now we're going to make use of that assumption. We're going to say, if this is true, and we showed it for one of them, if that's true, then this piece right here, it is 2k squared minus k. So that means this piece is also 2k squared minus k. This I can distribute. I can simplify a little bit. And you can do a couple things, but what I would recommend is get to this point all combined and then distribute that. Just see if they're the same. That's really the whole point, is make sure that both sides are the same. What that's doing is showing that the next term is still validated by the sum that you thought it would be, by the sum of that next term. So you're showing that they're equal, satisfying the idea that the next term is true. Watch your signs there. That's minus k minus 1. And that's it. Those are true. You've now shown that if you can start with one term being true, and you've assumed the next one's true, then the second one has to be true. But then the third one has to be true, because you've shown it in general for the idea of the next term. That sets up that whole sort of waterfall idea where it's just going to keep on falling and falling and falling. I hope that you have a better understanding for what mathematical induction does, that you understand that it actually works. It seems a little funny when you first see it, but after that, it really is a very powerful way we can prove a lot of these series that we find in this class and in calculus 2. So I hope that you enjoyed it. Hope you have a better understanding, and I will see you for another video.